Yes, yes, yes. This is the reaction mechanism that we had discussed in the last class. Okay. Uh, discuss that part. This would be here. Yes, 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 yes. Sorry, it was there in this first. Okay, okay, okay. Okay, okay. So this is a chain reaction. Actually, what is the chain reaction? I think you have some idea. A typical example of these chain reactions that we discussed here, that is hydrogen and bromine. They react in the gas phase to produce hydrogen bromide, right? And this reaction mechanism was proposed by M. Bodenstein and C. Lind in 1906. And they established the experimentally observed rate law. What was the experimentally observed rate law? That is that is this, right? They, on the basis of the experimental observations, Bodenstein and Lind, they established the following rate equation, differential rate equation, which is given by this, right? That is rate of formation of hydrogen bromide from hydrogen and bromine in the gas phase follows the this kinetics, means differential rate law. Now, this complicated explanation of rate law that appears on the basis of the experimental observation was later on explained theoretically in 1919, in 19th century 19 by J.A. Christensen, K.F. Hirschfeld, and M. Polanyi. They proposed the following mechanism to explain the above experimentally established rate law. Right. J.A. Christiansen. So this you can find in P.C. Roxith textbook. If you have P.C. Roxith textbook, there you'll get this part clearly. And also you can find in any other books if you are available, because these are the basic things you can find in any physical chemistry textbook, particularly in the graduate level. Yeah. Okay. So this is J. Christiansen, K. Hirschfeld, and Polanyi. They proposed the following mechanism to establish the above uh, rate equation. Okay, this will discuss. So they'll propose these five steps. This is very important. And these five steps together constitute what we call a chain mechanism. So that means hydrogen and bromine, that reaction in the gas phase takes place through these five consecutive steps, and they are typically called, say, first one, that reaction we call, that is dissociation of bromine molecule to bromide radical, to bromine radical, not bromide, but bromine radical, Br dot. And this is produced due to homolytic cleavage, as you know, that the bond is ruptured to produce the radical. And this is a chain initiation step. This we call a chain initiation. Second is bromine. Okay. Bromine free radical reacts with hydrogen to produce HBr plus H, free radical generated hydrogen. And this is subsequently followed by another step, that is step 2 and 3 together, what we call chain propagation. Why chain propagation? Because through these both steps you can find the formation of product, desired product HBr in the right hand side of these equations. So bromine and H2 react to produce HBr plus H. And H dot radical plus bromine react to produce this through where K1, K2, K3, K4, K5 are the constant of the respective reactions. And this step, that is step 4, we call chain inhibition. Means the product molecule reacts with another free radical of is the hydrogen free radical to produce back the reactant molecule, one of the reactant hydrogen, and here dot bromine free radical is generated. And finally, so look, step 2 and 3 and the 4, these are different because the products whatever are formed in produced or in step 2 and 3, that product partly decomposes to produce back the reactant molecule H2 and generates radical Br dot. And finally, in the step 5, we see the two bromine free radical, they react to produce back another reactant molecule, bromine. This we call chain termination step. So none of the reactions that proposed by the scientist all are unidirectional, right? There is no reverse reactions. The consider it in this mechanism. Right? So these are the 5 steps together, what we call the chain reaction mechanism. Okay? So you clearly write this. So this is very important. Sometimes in the midterm exam we ask what are the steps and label them like that. So if you could remember this, then you'll get that marks. Okay. So clearly you have to write all these steps and their name. So chain initiation followed by which is preceded by chain propagation, then chain inhibition, and then chain termination step. Okay. So may I proceed more? Hello. Do you have any confusion or any question at this stage? Okay. Now look, bromine and hydrogen radical that are intermediate species produced here, they are called reaction intermediates and they are highly active species. All these reaction intermediates, they are highly uh, uh, intermediate species. Okay. No, nothing other than so bromine and hydrogen, these are the reaction intermediates and they are highly active species because you know free radicals, ions, these are generally highly active species. Okay. Now for the, if we look at, as in the case of say steady state approximation, while you have learned that the intermediate species that appears in a sequence of reactions, their concentration will be very small. That means the rate at which they are produced will be exactly or almost equal to their rate of consumption or dissociation or disappearance. So their rate of appearance and rate of generation and rate of disappearance would be nearly equal, as you know. So let us find first what is the rate at which they are produced or the overall rate of accumulation of these free radicals. So for that we can write like this because in the first step they are produced, so we can write K1 Br2. Since all these steps are individually unimolecular, so the reaction order should be as in the stoichiometric ratio. So it is straightforward to write because one bromine molecule is involved to dissociate to produce 2 Br free radical, bromine free radical. So you can write the rate of formation of bromine free radical in the first step will be given by this first order rate equation K1 Br2. And in the subsequent step, means second step, that bromine radical reacts with H2 molecule to produce that HBr and H radical. So since Br free radical produced in step 1 is consumed in the second step, so naturally, and the stoichiometric ratio they are produced in 1:1 ratio, so these reactions will be treated as if a second order reactions and first order with respect to each of the components, that is bromine and H2. And since bromine free radical has been consumed, so it would be negative sign. Plus, in the third step, you see hydrogen free radical reacts with bromine to produce H free radical and HBr. Right? So we can write like this in the third step because H and Br2 reacts to produce HBr plus Br dot. So since it is produced, so again in the third step, since bromine radical is generated, it is positive sign, the rate of its formation. Now in the next step also, hydrogen reacts with HBr to produce H2 and Br dot. Just see step 3 and 4, both these reactions, bromine free radical is generated. So that's why both are positive sign, step 3 and step 4. And in the last step, again, you see bromine radicals, they are arrested to produce back the reactant molecule Br2. So naturally, you expect that there is also second order reactions because two species are involved, and we can write like this. Now, as if we apply the steady state principle, that is overall accumulation or net accumulation of Br free radical, that would be equal to 0. This is under steady state approximations that we can write. Exactly following the same procedure, another free radical, for another free radical, hydrogen free radical, we write this equation dH is equal to in the same way, similar way, right? Because in step 2, hydrogen free radical is generated with a positive sign. In third step, hydrogen free radical reacts with bromine molecule to produce HBr and Br dot, so it is negative sign. And in the fourth step, again you see hydrogen free radical has a sign, so it is a negative sign. And it would be equal to 0. Okay. Now you add these two equations. Do you have any question? Please clarify at this stage. Hello? Hello?
Yes, sir.
Can you hear me?
Yes, sir.
Is it all right or you have any difficulty at this stage? Just to apply steady state principle or approximation on the reactant, on the intermediate species, that is free radicals H dot and Br dot. Right? Net accumulation we have equated to 0, means the rate at which these free radicals are generated will be almost equal to the rate at which they are consumed in subsequent steps that I have shown it here. Okay. Now, if you add these two equations, or these two steady state equations, so interestingly, the expressions would be very simple and straightforward like this. Just it would appear like this. And from these expressions, we can express the concentration of this bromine free radical in terms of the reactant bromine molecule. Right. This active species concentration can be equated to this corresponding stable bromine molecule. Okay. And this quantity, that is ratio of these red constants raised to the half, that we put is another constant. Just to simplify, instead of writing down explicitly all these red constants, I put like this, nothing else. So basically K6 is equal to square root of this ratio, that is K1 by K5. Okay. Now from equation 2, that is dH dt equal to 0, from this expression alone, one can write the one can express the concentration of hydrogen free radical, right? Hydrogen free radical in this form. And in the right hand side, you see all the species are stable excepting Br dot. So we now substitute this expression of bromine free radical concentration here in the numerator with that expressions, that is P6 Br to the power half, that we put it here and simplify. And ultimately you get an equation like this, where we have substituted bromine free radical equal to P6 Br to the power half. It would be actually, so it should be actually 1 upon, it should be clearly written 1 by, sorry, so problem, 1 by 2. Okay. So if you look at these expressions, that is, we have been able to express the hydrogen free radical concentration and bromine free radical concentration in terms of the stable species. That is either H2Br2 or HBr. If you look at carefully, bromine free radical we have been able to write in these expressions, that is Br2, and here H dot we have been able to write in this form. Now let us find what is the rate of formation of HBr molecule, that is product. And naturally you can see that in step 2 and 3 it is produced, and in the subsequent step 4 it decomposes or dissociates. So naturally the overall rate of formation of hydrogen bromide, right? This can be written as sum of the rates by which it is produced, that is step 2 and 3, and that should be reduced by the step 4 where it has been consumed or HBr dissociates, right? So that you have written. This is the overall rate of formation of HBr. Now since we have now the hydrogen free radical concentrations and bromine free radical concentration, the intermediate concentration of the intermediate species that we have obtained in terms of stable species and put in this equation. But before that, again we simplify. This is very important from equation 2. If you carefully look at from equation 2, by simple manipulation, that K2 dr2H2 minus K dr this is equal to K3 this. So by simple algebraic manipulation of equation 2, we get these simplified expressions of rate of formation of H to K3H. This is very interesting. So we have been able to express the rate of formation of hydrogen bromide, yes. The rate of formation of HBr in the gas phase can be written that is equal to K3 to K3 hydrogen radical concentration into Br2. Now hydrogen radical concentration, if you put in these expressions, then it appears to be expression which it seems to be somewhat complicated like this. And this K3 term, if you want to remove from numerator and manipulate, then we can write like this, because if you take K3 common here, then it would be K4 by simply K3, like that. Okay. And then this K3 term cancels out. And we get this simplified expression of the rate of formation each year. Right? And again on simplification, that is if we collect this product of two rate constants and the ratio of these rate constants by K and K prime, then this equation right hand side would be like this, right? K is to be at 2 raised to the power half, and in the denominator we write 1 plus K prime into HBr by bromine concentrations. Okay, now this reaction, this expression that we deduce from this set of reactions following this mechanism, that is considering 5 consecutive steps as proposed by those scientists, we ultimately have been able to write the rate equation which exactly conforms to that established by Bodenstein and Lind. That is experimentally observed differential rate equation. Is it clear? You just compare that experimentally observed rate law with these theoretically deduced rate expressions that was proposed by Polanyi et al. Yes? Do you have any confusion or any question, please? The derivation is very simple and straightforward. And manipulation, you have to just remember, it is also not difficult. But while simplifying these expressions, rate equation, this step is very important, right? This identity, right? Okay. Now, the thing is that, as you have noted, to simplify this, let us consider step 3 and 4. These steps, look, these are competing. Competing means, say, HBr is produced in the first step, while HBr has been subsequently decomposes in the subsequent steps. So that's why these two steps means H free radical, hydrogen free radical can collide with one molecule of bromine, or it may collide with a product molecule HBr, because you are carrying out these reactions in a closed chamber or a vessel where these H free radical have a chance to collide with available bromine molecules or the reactant molecules HBr that is produced. Right. So if HBr collides with bromine or HBr, then uh, these steps that will products that will be formed has been shown in the right hand side. So that I am telling you, they are competing with each other. Okay. Now, what is the rate expression of 4? What is the rate expression of reaction 4? It is given by rate subscript 4, that is equal to K4H HBr. And rate 3, what is the rate equation for step 3? That is K3 into concentration of hydrogen free radical electron. And this can be written that is equal to K4 by K3. And this hydrogen free radical has been vanished. So we are left with this expression K4 by K3 to HBr in bromine. So this is very interesting experiments, right? Which is the ultimate expressions. Now, at T tends to 0, what happens? At the very beginning of the reactions, there is no product, so we can write this. Right, at the very beginning of the reactions, concentration of HBr is always 0. And so the rate of formation of HBr we can write in this form. Same expressions, same rate equations, because if you follow these expressions, because HBr tends to 0 means the rate equation has been reduced to KH20, Br20 to the 1 half, and the denominator only 1 will be there. So it will be simplified expression. When, and in that case, this rate of formation of HBr we label as 0 means at the very beginning. That is at the very beginning of the reactions, chain reactions, right? Uh, when the concentration of HBr is nearly 0, the complicated rate equation, the differential rate equation simplifies to this form. And naturally, as you may expect that, what is the overall order of the reactions now? It is 3 halves. 1 H2, 0 means concentration of H2 0 at the very beginning of the reactions. Likewise, Br2, the subscript concentration 0 indicates the concentration of bromine at the very beginning of the reactions. So, at the very beginning of the reactions, the rate of formation of HBr, that is we call initial rate law. It has an overall order 3 halves, right? That is first order with respect to hydrogen and half order with respect to wind. Okay. Now, if you plot from this equation HBr versus T, then what is the slope of the reactions? Because H20 and bromine 0, they have certain value. H20 and Br20, let us consider as if they are initial values of concentrations, right? So if you plot HBr versus T, it should be as if which kind of reaction kinetics it follows on the graph, can you say?
Zeroth order.
Yes, it is zeroth order, right? And the corresponding slope is equal to 6 this product, right? Where we have written k equal to 2k, 2k1, k5 to the half. So this is the kinetic study of these chain reactions between hydrogen and bromine molecule in the gaseous state or in the gas phase to produce hydrogen bromide molecules. Okay. Now the next question comes. Similar things are there for HCl molecules and hydrogen molecules. Now the question is HBr we have shown. Now the next question, whether H2 and chlorine to produce HCl, hydrogen chloride in the gas phase is possible or not. Likewise, whether hydrogen and iodine molecule they react to produce HI, hydrogen iodide in the gas phase through chain mechanism. Yes or no? Interestingly, this reaction, that is formation of HI from H2 and I2, does not follow this chain mechanism. That is very interesting. But of course, hydrogen and chlorine, they will react to produce HCl through chain mechanism. Of course, at the very beginning, the chlorine free radical may be generated either by dissociating chlorine thermal instead of thermally, but in presence of light with definite photon, chlorine may dissociate to produce to chlorine radical. Or this chlorine molecule may react with sodium vapor to produce or degenerate with chlorine radical in the gas phase. And naturally, other remaining reaction sequence that I have not shown it here, that is chain mechanism that we have just shown for hydrogen and bromine reactions. Exactly follows the same set of mechanism. And it is written that 10 to the power 6, what is the importance of chain reactions? You see, about 10 to the power 6 molecules of HCl are formed from each chlorine free radical. For each chlorine free radical, there is part one chlorine free radical is efficient to produce 10 to the power 6 number of product molecules that is HCl. So how efficient the chain mechanism that you can learn from here. Now the next question, hydrogen and iodide, why it does not follow the chain reaction mechanism? For that, I think probably you know the answer. If you look at, if you compare the crucial step, that is the second step, how the hydrogen halides are produced, right? This is the second step. And you see, in this crucial step, PA means activation energy appears to be like this. Where EA is nothing but this is the activation energy. Okay. Now you see activation energy is in the case of hydrogen and iodine about 33 kilocalories, whereas bromine is to 18 kilocalories and chlorine and is to 5 kilocalories. Of course, these are kilocalorie per mole. So that means hydrogen and chlorine reaction should be much faster, following the same chain mechanism. Whereas then bromine and hydrogen molecules react like that. But hydrogen and iodine molecules, they will never follow this chain mechanism because of higher activation energy involved in this step 2, that is chain propagation step, that is the first reactions in the chain propagation step. Clear? Why hydrogen and iodine molecules in the gas phase do not react to produce hydrogen iodide? Because of because it involves higher activation energy compared to other reactions. Right? Now I have given a simple uh, reaction and you try to deduce the rate law, this differential rate law, where the reaction is 3/2 order. So deduce the rate equation or reaction rate for the following reactions. I have given the steps are given. Right? First step is the chain initiation. Second step is that COCl is produced. And in the third step, the COCl radicals so far generated again react with chlorine to produce COCl2, the desired product that we call a zinc, COCl2 or zinc. as chlorine free radical. This is chlorine free radical. And again, this chlorine to chlorine free radicals we combine to produce the three chlorine molecules. So this is the set of reactions, and you have to predict you have to deduce the rate equation, right? You have to produce the rate equation. You have to deduce that the concentration of COCl2 due equal to KCO Cl2 divided by. You try to deduce this, right? Following the similar procedure that we have done earlier. But we have to find out what are the intermediate species. That is very important. Where you can apply chemistry. Okay. So yes, so you can. This is the overall reaction. CO reacts with Cl2 to produce COCl2. This is the overall reactions that you can do. And this is the 4 steps that I have given to you. Oh, sorry, this is another mechanism, another reactions that you can write down. That is rate of formation of acetaldehyde. This is another problem, right? The reaction is this. That is decomposition of acetaldehyde to produce CH4 and CO. Okay. Both these reactions are available in PC Roxy, GW Castellan. Okay. In these books you can find. Everything is there. Or you can write and try yourself, do yourself. At home assignment. Okay. So that's all. Hello. Please response. Are you getting me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
So these you can
Yes.
find, all these reactions mechanism you can find in PC Rocket textbook. And if you have any difficulty to derive these equations, so in the next class we'll clarify. Okay, first write this reaction mechanism. Steps you write. And what are the intermediate species that you have to write? CH3 and PPDCA. These are the reaction intermediates. Okay.
Sir.
Yes.
Sir, please please share the notes in classroom?
Notes cannot be shared, right? Notes cannot be shared because most of you are reluctant, right? Because if I proceed, then many of you will not attend my class, and ultimately in the midterm, you see, in the not only midterm, your performance is very poor in general for some departments, and this is unfortunate. Every year I have noted, and you see how many of you are attending this class. You can find it now. You just see yourself, right? How many of your friends attended to this class, right? How many? Very few. Out of 90, how
61.
many? Then out of
61.
30, so 30 or almost 30 of your friends, they're not joining. Why? So they are not interested. Now your future is not so clear. Accepting CST and IT departments, recently the job scenario and future prospect is very not clear unless you have a education, right? For other core subjects, you have to be hard labor and competitive. In India, you may not have opportunity, but all the departments you have find plenty of opportunity in abroad. After your graduation degree, if you have decided to go to abroad, then you have plenty beyond your expectation. You will get several opportunities after your master degree. But in India, it is very difficult. It is highly you have to struggle hard. That is my advice. Okay.
Okay, sir.
Sir, I have a question.
Okay,
Yes.
sir.
Any
Sir,
question?
the sir bromine molecule react to 10 to the power 6 time, as you said, but
Not bromine molecule. 10 to the
chlorine.
power 6 HCl molecules are produced from one chlorine free radical. That means
Yes, sir.
one chlorine free radical may produce about this much, this number of product molecules. So that means
But sir,
HBr is highly powerful reactions, just like chain reactions in nuclear fission,
yes,
similar
sir.
to that. Yes.
Sir, but why after 10 to the power 6 time? As why
No, no, no.
chlorine molecule?
It is not my prediction. It is the experimental observation, right?
Sir, is
It is
it
an,
due to the activation energy decrease? No.
there is a term chain length that we discuss in the next class. From that, you can explain why it so happens, right?
Okay,
It
sir.
depends on the relative ratio of the rate constants. That factor will
Sir,
be there.
sir,
Okay?
how in the test the number of molecules are counted? I mean, so precisely.
By mole
No, no.
number.
If you calculate the number of moles, then you can calculate the number of molecules by multiplying it with the Avogadro number, right?
Yes,
Okay?
sir.
You first go through this, and then the next class you ask whatever question you feel or appears to your mind, you just throw me. Okay? No problem. Okay. So plenty of opportunities are there if you have to focus to go abroad. India is a small country, but besides you, there are right several countries are there, several opportunities are there, right? Only you have to know the subject thoroughly, whatever discipline you are getting here. So don't be worried. Okay. I think you are confident enough because you have secured this position in this institute. So I think you can do a lot if you like. Everything is rested upon you. Okay. Your decision is very important. Your mind is very important. Okay. So no more today. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.